IEEE CIS webinar, which is sponsored by the IEEE CIS. Today we have Professor Antonio LaTorre from Universidad Politécnica de Madrid. Okay, sorry. And he is also a director of Center for Computational Simulation. And his topic today is going to be ZEBAI, Evolutionary Algorithms for the Design of Zero-Emission and Cost-Effective Buildings. So if you guys have any question, you can type it in the chat box and we can answer it after his talk. So please welcome Professor Antonio LaTorre.
Thank you, Sansani. Thank you everyone for joining us today. So as Sansani mentioned in the introduction, I'm going to talk about the work we are doing in the ZEBAI project. We are trying to solve, or not actually to solve, but to contribute with a problem that has a very high impact in our societies, which is the reduction of the CO2 emissions associated to the construction industry. Sorry. Okay, this is the plan that I have for this presentation. So first, I'm going to briefly introduce the context of the things I'm going to share with you today, which is the ZEBAI project. This is a project funded by the European Union, and it will last for 3 more years. We started in 2024, and it lasts until 2028. It is a bit misleading timeline because it seems like a very long project, but we are actually in the 2nd year of execution of the project, and we are finishing the implementation of all the software-related tasks. And then we have 3 more years for the execution of the demonstrator, in which we are going to test that everything we are developing actually works and it's useful for architects and designers carrying on these demonstrators. So first, I'm introducing this context, and then I'm going to present, this will be the core of the presentation, a couple of applications within the project to 2 specific parts of the design of a building, which are fenestration systems and facades. Then I will briefly share how we have designed the software architecture to automate and to be able to replicate the results that we have in our simulation, because it is a complex software architecture in which there are many software components, either in home developed libraries and also third-party libraries and software, and everything has to play nicely with each other and communicate. And thus we need a control system to run all our experiments. And finally, and as this is intended to be useful for real-world users, we are also, in parallel to the core optimization technology, we are also developing a user interface. So we showed you just a little bit of what we plan to provide our users. This is still a work in progress prototype. It's not finished, but it somehow helps to see how a user would interact with this tool. So what's the ZEBAI project? Well, the ZEBAI project is intended to help architects and designers to improve their designs of zero-emission buildings. And there is a rationale behind this. The first point is that there are estimations that 25% of global CO2 emissions are caused by the construction industry, which is a lot. And on the other hand, the European Union has pronounced a directive that for 2050 they want to reach climate neutrality in our country. So the challenge here is that we are not progressing adequately. Current progress is very slow. Most buildings that are being constructed right now are not focusing on emissions. If we are lucky, they have in mind energy consumption, which is not the only part associated to emissions, but for most of them, normally promotions just focus on the cost of building or constructing this building. So there is a lot of work to do. We have, it seems that we have much time. 25 years seems like a lot of time, but these changes take a lot of time to be accepted. And this is something that we are experimenting ourselves with our demonstrators, because we have long, insightful but long discussions with architects and designers on how a tool like the one we are developing could be useful for them to improve their design. So the project has several objectives. The first one is that we want to develop a heuristic methodology. We want to integrate in the methodology several aspects of the design of zero-emission buildings, not only focusing on the energy consumption of the building when it is operating, but also on the amount of energy that it demands for construction and the emission associated to the construction itself and the transportation of materials to the location of the building. And of course, we also are interested in minimizing costs. So this is, in other terms, a multi-objective optimization problem. And to solve this problem, we are using evolutionary algorithms. And as I mentioned, we use them to deal with all these objectives at the same time. We optimize the selection of materials that will be used during construction, especially those affecting the envelope of the building. We select which active and passive systems are being used, or everything related to HVAC, for example, is being considered in the optimization. And our hope is that this will help to make the design faster, easier, and more eco-friendly, more efficient. This third objective is related to the development of a materials database. This is not as related to the presentation I'm doing today, but if we want to be able to optimize and select among a set of materials and systems, we need a catalog of those materials and systems. So one of the key work packages of this project is the collection and curation of materials from different locations in Europe. Our demonstrators are all of them located in Europe, in 4 different countries with different climate conditions. We have one in Spain, another one in the UK, third one is in the Netherlands, and the fourth one, and the most complicated one, is it's located in Ukraine. So all these locations have very different characteristics. Their climates are different. The usage of those buildings will be different. So we need curated material database that covers at least all the materials and systems that are available in those locations. And if not all, at least a representative amount of them. And in the end, our final objective is that we want to be able to provide a tool that helps architects and designers with the design of their buildings across diverse climates, usages, and building patterns. That's what we hope to reach by the end of the project. So this is what current design process looks like at the moment. There are different actors. They focus on different aspects of the design of a building, and they not always speak the same language. And there are problems in communicating suggestions or changes from one aspect of the design to the others. And this leads to inefficiencies and delays. And sometimes what normally happens is that not all the suggestions made by the last actors in this chain are taken into account due to the time limits, constraints that normally construction projects face. So we have first the architect that design the geometry and select a preliminary at least set of construction systems for the building. Then we have engineers that make the definition of all the mechanical systems in the building. There are normally, in the case of of zero-emission buildings sustainability consultants that analyze the impact, the environmental impact of the current design. And there is also a specialist in renewable energy that suggests how these systems can be implemented in the project. So all these actors make suggestions which imply modifications to the initial project. And it's difficult to implement all of them before the last person in this chain, the specialists from the certification of sustainable buildings person reaches the project and joins the project and tries to certificate if this project meets all the requirements to be considered a zero-emission building. So this makes this kind of project complicated, and integrating all these contributions in the design of the project can be very challenging. So limitations identified in this process are the lack of an integrated analysis. Each of these actors are experts in their own field, but as I said before, they not always speak the same language. So suggestions made by one of these people and not always are successfully implemented, at least not as they had in mind in the beginning. There is no curated materials catalog. So when we started conceiving this project and we were planning how it would be structured, we didn't. In the beginning, we were not sure if we needed this work package for the curation of the catalog. We started to search for public databases, and what we observed is that there was no database that covered large enough set of materials and systems, and of course not across different countries, and not with all the properties that we need to simulate accurately their behavior when we design the building. So that's why we needed to create our own catalog, and that's what we are doing now. The third limitation that we identified is that in the end, to automate all this design process with Evolutionary algorithms, we rely on simulators. And simulators are simplifications of real life. And we observed that there were some discrepancies between the results that those simulators return and the values observed when monitoring buildings in their operation. So one of the tasks that we are also doing during the project is to develop models of the errors between the simulation parameters obtained by the software we are using, that is Energy Plus, and what we measured when we monitor that building in its operational phase. And we are going to use those models to correct the output of those simulators to provide more precise, more accurate results. And finally, I have to admit that I didn't know which picture to use in this slide, so I just looked for something that looked very old. And this fourth limitation is that a manual approach to the design of these kind of buildings is time-consuming, error-prone, and we wanted to replace it with something that could provide not only accurate solutions, but also novel solutions. Because one of the things that we have found out in our preliminary experiments is that some of the design suggestions made by EAs are, let's say, unexpected for architects. So I will go into this when I present the design of fenestration systems. So in the end, what we want to reach with this project is a tool that helps designers and architects to reach their objectives by not by replacing them, but by helping them to make this design. So in the end, we need to somehow include all the knowledge of the expertise these professionals have from years and years of career into a tool that provides some designs that can be further verified by these experts and then implemented in real-world scenarios. As I said, we need to provide the tool some inputs that help the design process to consider all the aspects relevant in this process. So first, we need to provide information about the building we try to design, and I must note here that at least in the context of this project, we are not considering the structure of the building. The structure is already given by architects, and we are focusing on the envelope of the building and the active system. So we affect the walls, the roofs, shading systems, fenestration systems, of course, all the HVAC systems, but we don't play with the structure of the building. It has a structure, a number of rooms, a size, and so on. But everything else that affects the performance, the energy performance of the building, is modified by our tool. We also need to provide information about regulations that affect the design in the country in which the building is going to be located, because different countries have different regulations and some countries have no regulations at all. So we need to know that from experts, and for example, there are some limitations to consider building as energy efficient depending on the country. There are also different parameters about comfort. For example, in Spain, we target a 22 degrees temperature in winter and a 25 degrees Celsius temperature in summer, but that could be different in other countries. So all this needs to be provided, and we are gathering this information for the different locations in which our demonstrators are located. And this is taken into account during the optimization to evaluate how efficient and how compliant with regulations our designs are. We need, of course, also environmental information about the weather in the location in which the building is going to be constructed. And we also need the BIM design, which is the digital design of the building with the structure with which we will play and modify all these aspects I mentioned before. Regarding the weather conditions, one of the things that we are considering, it's not really fully implemented right now, but it's going to be in the near future. We have done some tests, but it's not purely integrated in our workflow, are future climatic conditions. So when designing a building, you have to take into account that it has a lifespan. And the problem that we're facing now is that in the lifespan of a building, that it can be, let's say, 50 years, things could look very different in the context of climate change that we are facing now. So we are, I will mention this later, we are considering the IPCC RCP, several of these scenarios that try to predict or to provide an estimation of what are going to be the conditions at different locations regarding on how efficiently we deal with climate change. And those are the inputs that we need. And then this is the kind of analysis we do during optimization. So we simulate the energy efficiency of the building. So we basically create different designs with different materials and systems and simulate how efficiently this design performs. We also include this resilience analysis with different climate scenarios. We simulate for comfort and air quality. There are some regulations here, as I mentioned before, that limits the number of hours of discomfort that a building can have, depending also on the usage. It's not the same a building that it's used for for residential use than a building that is being used for another kind of service, a public building for a hospital or a school have different regulations. We also account for the carbon footprint and circular economy aspects. In the catalog of materials that we are developing, we also include information about these parameters, not only their cost, not only the physical properties, but also about the carbon footprint and how efficiently we are getting those materials from local manufacturers, for example. And of course, we also account for the cost of materials. So in the catalog, if each material has a cost associated, and one of the objectives that we optimize is the cost of the final design. There are also some associated analyses that are being executed during the optimization. Well, not during the optimization, but associated to optimization. One I mentioned before is the error modeling and correction. We have a set of retrospective cases that we have analyzed, and we have modeled the error between the simulation and the monitoring data of those buildings. So basically, we have the design, the digital design of the building that we can simulate, and also those buildings were actually constructed, and we have some monitoring data on the operation of that building. And we have been modeling the error of the simulators on those cases, and we are developing models that can be applied to new scenarios and see if we can correct these biases that are present in the simulators. And we are also developing surrogate models within the optimization library. They are actually developed. And these models are basically intended to reduce the computational cost of those simulations. So basically, to put this into numbers, the simulation with Energy Plus for the efficiency of the building, the energy efficiency of the building, to calculate the heating and cooling demand of the building, can take some time between minutes and hours, depending on the complexity of the building. For the simplified building that I'm going to show today, it takes less than a minute, maybe between 20 and 30 seconds per simulation. But for more complex buildings, one of our demonstrators, for example, is a hospital that has several thousand square meters. So that we don't have still the model, so I cannot provide exact numbers, but I estimate that it will be in the high minutes, probably close to hours. So we need these surrogate models, and we are making our tests, implementing them. They are implemented as machine learning methods. We are using trees models and ensemble models to estimate the cost of those, the demands of those buildings without actually running the Energy Plus simulations, and well, we have some good results there. So this is a summary of the process. The items in yellow are our inputs. We need the design of the building. We need the catalog of materials. We need regulations for the location of the building. We need information for the environment and weather conditions of that location, and we need the BIM design. Then we run several simulations or computations of different objectives when designing these buildings. We apply the error that we have modeled to correct the predictions of the values returned by the simulators. And then once we have a final result, it will be implemented in the demonstrators that we have in mind. So this is basically the context in which this project is located. And now I'm going to present a couple of case studies that we have been working in the last months. The first one is the automatic design of fenestration systems, and the second one is the one that we are currently working now, which is the design of the facades, the walls of the building. This is the the floor plan of the apartment, the reference apartment that we're considering. This is a small apartment for a small family with one double bedroom, one single bedroom, a bathroom, living room, and a kitchen. And it has 4 walls or with the four cardinal orientations. There's a north facade for the living room and the kitchen, and there's the south facade for the 2 bedrooms. And we are locating windows also in the west facade for the bathroom. So basically, we are optimizing the building to locate and design the 5 windows. Depending on the building, the number of windows can grow, and that also will make the problem more complicated, as each window is optimized independently. Depending on the use case, this could be the case in other buildings with more regular shapes. Some windows could be tied together, so they are optimized all together. But in the end, the number of parameters to optimize will also grow. And we are optimizing the same building in different locations. So for now, we are focusing on 3 locations in Spain with different climate conditions. We have Seville, Madrid, and León. And this map represents the climatic areas in Spain. There's something similar for most of the countries, at least in Europe. And this visual encoding is associated to a letter and a number. The letter represents the severity of winters, and the number represents the severity of summer. So the higher the letter or the number, it represents a more severe winter or summer. For example, in Seville, we have mild winters because it's a B, but we have very hot summers because we have a 4. In León, we have the opposite. There is an E, very cold winters, and 1, very soft summers. And there's the case of Madrid, which is the worst case scenario, in which winters are cold and summer are also very hot. And there's that alpha on the right, the red one, which is a very specific climatic area for the Canary Islands that behave completely different to the rest of Spain. And these are the RCP scenarios I mentioned before. In the results I'm presenting today, these are not included. I didn't have time. I don't think I could make everything fit in this presentation. But this is something that we are also considering. We are considering the current conditions of the different locations, and also RCP45 and RCP85 scenarios. So for each location, we have these predictions that try to model the consequences of our acts depending on which actions we take. So depending on the scenario, we make a higher or a smaller effort to mitigate climate change. And the worst case scenario, RCP85, means that we don't do anything to deal with climate change, and it could lead to a rise in temperatures of estimated of almost 4 degrees in average. For the RCP45 scenario, it's almost 2 degrees in average. And well, those are the 2 that we are going to consider during the work. So for fenestrations that I mentioned before, I don't know about you. I always make the joke that I'm working on an architecture project, let's say, but I'm a computer scientist that works in a computer architecture department. So sometimes people are confused. This is a computer architecture project or real architecture, let's say. So for me, many of the words that I'm using today were completely new like 2 or 3 years ago. And this is the case for all the elements that are affected when designing a fenestration system. So this is a representation of a window, really, actually a fenestration, in which we have many different elements with which we can play. In our designs, as this is the the most common approach nowadays. We are considering double glazed systems. This means that we have two glasses with a gap, and in this gap we have a gas. This gas could be air or could be a different kind of gas. Of course, this should be sealed to avoid to favor the isolation properties of that gas. So we have two glasses, one on the front side, which is to the exterior of the building, one to the front side, which is to the other side, sorry, which is to the internal part of the building, and this glass in the middle. But designing a fenestration system has a lot of more properties to decide. So we have on the left lateral view of the side view of the fenestration system. We have the walls, the upper and the lower part of the wall, and there are some revealed surfaces, which are the part of the walls that get exposed to both sides of the window. We have the glazing systems that I mentioned before with those two glasses. We have the frames for the glazing system and also for the surroundings, and we have also the seal depth in the lower part of the fenestration system. Apart from this, there are some regulations regarding how big or how small a window can be, and also where windows can be located. So we have several constraints that affect how we can design those windows in the real world. Apart from a window normally associated to a fenestration system, we have a shading system. This shading system helps reducing the amount of heat that gets into the building. This shading system can be movable, for example, with blinds that can be activated or retracted, and we also can play with the angle of the slats. This is something that we can manually activate or even automatically activate. And there are also some fixed shadings systems such as overhangs and fins that we can only install and let them operate. So when designing a fenestration system, we consider all these variables, and each of them has a range of valid values that can be considered. In the end, for the design of this 5 windows building, we needed to consider 69 variables. The objectives that we had in mind when we ran this optimization were minimizing the energy demand for heating. So basically the energy demand during winter, minimizing also the energy demand for cooling, and minimizing the hours without thermal comfort. As I said, in Spain, regulations target to 22 degrees Celsius in winter and 25 degrees Celsius in summer. We had a discussion when deciding how to approach this multi-objective problem because, well, in the end, we could choose either a real multi-objective algorithm, but this wasn't easily accepted by our final users. So they wanted to have more control on the weights associated to each of the objectives. So in the end, we ended implementing this as a single objective problems composed of multiple objectives that are manually weighted by our users. This is something that maybe in the future we could integrate other multi-objective optimization algorithms, but for now we try to satisfy the request of our final users. There are also some regulations and constraints that I mentioned before regarding the efficiency of the materials that are being used, the locations and size of windows. Everything is considered, and we apply penalties to designs that don't meet those constraints and regulations. And we made some assumptions, and we were focusing only in the design of fenestration systems. We fixed the HVAC system. It is an ideal load serve system. This is a system that can theoretically provide infinite capacity to reach our target temperatures. And also, we didn't integrate renewable energy sources in the design, so it's very difficult to design a zero-emission building without these energy sources. But we didn't want to make the problem very complicated, because we wanted to focus only on windows. There's also another assumption that I forgot to put in here, which is that the materials used for walls and roofs were also fixed, so we didn't optimize them, and we could also gain some more performance from the optimization of those parameters. So basically, this is the overview of the problem we are solving. We prepared a catalog only of Windows components, including materials for the windows and frames, and also for the shading systems. We encoded the rules to comply with regulations, and we provided the weather and location information for our 3 locations, and also the geometry of the building that I showed before. And we computed during our optimization the energy demand, both for heating and cooling with Energy Plus. We also computed the comfort indices according to the regulations in our locations. And we also included a first simplified cost analysis, in which we associated a simple cost associated to the amount of materials that we were employing. So all materials are considered to have the same price, which is not, of course, accurate. And we wanted to minimize the amount of material to be used in the design. And as our optimization algorithm, we use shade with local search, and we also included restarts when the algorithm seems to stagnate. And we ran this for these 3 locations, León, Madrid, and Seville. We ran, I think, 15 simulations with 30,000 fitness evaluations as the convergence criterion to stop the optimization. So we played with the glazing side, with both width and length of the window. We modeled this detailed glazing composition with double glazing systems and this air camera in between. We optimized for frame materials. We considered both fixed and movable shading control systems, and obtained some, let's say, interesting results. So first results I'm showing here are the fitness values in log scale for the aggregate of the different objectives: heating, cooling, comfort time, and simplified cost that I mentioned before. And results that I'm showing here are the comparison of the algorithm we are finally using, the shade plus the local search, compared with a baseline, which is a genetic algorithm. We actually ran multiple optimization algorithms in our experiments, but well, these plots here compared shade with GAs, because that was requested by one of the reviewers of the paper in which we communicated these results. And we saw that we consistently, with the shade, outperformed the performance of genetic algorithms for any of the locations. And not only we obtained better results in average, but also the robustness of the optimization results was better. So what you see here is the median results with the solid line, and dashed lines represent 70 and 95 confidence intervals of solutions. So the dispersion of the GA is much bigger in these results. And this is also the case for Seville. So basically, it seems that we made a correct decision when we chose this algorithm, at least from the convergence point of view. Another interesting result is that the algorithm actually converges normally to very similar solutions. So when analyzing some of the parameters of the glazing systems that were installed, solar control type, the U values, which is the thermal transmittance coefficient of the windows, and other parameters such as the solar reflectance or others, we found that most of the runs converge to the same values. So basically, the search was actually following was actually working. We were actually optimizing. We were not randomly search and created solutions because, of course, all the 15 runs were randomized in the beginning, and basically we converged to the same kind of designs for the same scenarios. Oh, sorry. This is an example of the output of the tool. So basically, we provided something with which the architects or the designers can work. We provide detailed information on the kind of glasses and the kind of gas that they can use for the design. And this is something that we provide not only in a raw text file, but also we can export this to a format that can be reviewed with this user interface that I'm going to present later. We also had other interesting results. We tested a couple of scenarios. Scenario S1 allowed for all shading systems to be selected, and S2 only fixed shading systems, and we showed that allowing for movable shading system was actually contributed to reduce both heating and cooling demand of the buildings. It is true that in the case of cooling demand, without renewable power sources, it was impossible for us to reach the upper acceptance limit imposed by the regulations, neither for Madrid nor for Seville. But this is an expected result, as renewable power sources are a key element in the design of zero-emission buildings. And regarding the no comfort time, we reached both in León and Madrid the target of I think it's 480 hours per year, I think. And not in Seville, especially during summer, but this is also something expected as no renewable power sources were allowed, and thus we couldn't satisfy all the demand during summer. And regarding the size of the windows in the south facade, we also observed an interesting result as we obtain consistently bigger windows when we allowed only for a fixed shading system in León, and but this was the opposite in Madrid and in Seville. Smaller windows were used or were returned when only fixed shading system were allowed, and this is somehow counterintuitive for the designers, as they expected these windows would be bigger. And we had some discussions on how this, why this could be happening. And well, in the end, what we more or less agreed is that somehow the algorithm was compensating the increased demand during the summer with a reduction of the demand during winter. So that would be the reason behind this. And well, this is the convergence of the glazing systems selected in the different scenarios. When more shading systems were allowed, there was a more clear convergence towards particular solutions than when we didn't allow for them. But this is something that should be further studied. Regarding the cost reduction, I have to remind that this is a very simplified cost model, but we could observe that we were able to reduce by 20 to 40% in average use of materials. And I must highlight here that the cost is only considered when we are meeting the heating and cooling demand. So in those scenarios in which this is not satisfied, we try to further improve to reduce heating and cooling demand before getting into optimizing the cost. So in conclusion, we were able to meet regulations mostly and reduce energy demand and cost in many cases. And we need to include renewable energy sources to further decrease cooling demand and hours without thermal comfort. Of course, optimizing walls and roofs at the same time could also make a difference in the final results. And we also need a fully fledged cost model to provide accurate feedback to designers, because this model is not is only a very simplified scenario in which we assign the same cost to all the materials. This is the reference, just in case you are interested in reading the full details of this experiment. And I wanted to continue with a second case study, which is the design of facades. This is the part of the design that we are working now. When designing a wall seems a simple structure, but there are many different approaches to designing walls. This is something as I mentioned before, I'm learning during the last 2-3 years. So in our models, we have integrated 3 different approaches for the design of facades, which are called ethics, opaque ventilated facades, and prefabricated facades. The last one, prefabricated facades, it's been incorporated recently. This is not included in the experiments we have conducted so far, and this has been requested by one of our demonstrators that wanted to study. They don't have experience in the use of this kind of facades. They wanted to study this within the demo. It's not only that we have 3 different types of facades, but also each of these facades can have different designs themselves. So depending on the number of internal layers, the number of the type of support layers, the number of air cavities that they have, there are different approaches to that. We have this first system ethics facades. In this case, insulation is placed in the outermost face of the facade, so it's facing directly to the exterior. They are more cost efficient. They provide limited protection against humidity, and they are suitable for dry climatic regions. These are some examples of the approaches. As I mentioned, some of them have cavities, some of them don't have it. They can have different numbers of internal layers, different types of insulation materials. So we have a large range of designs to choose, because we not only choose which of these designs we need to test, but also which materials for each of the layers we are considering. And something similar happens for opaque ventilated facades. This is a different design in which at least 2 opaque layers are separated by an air cavity that is ventilated. This means that the air flows by convection to help reducing the moisture of the building, and also to improve the overall efficiency. These are more expensive and complex to install, but they are more efficient in those scenarios. And again, we have different designs with different number of layers and different number of air cavities, internal layers, and of course, materials for each of them. So our problem here was how can we encode solutions for this part of the optimization. For Windows, it was easier because we have a window, so we need to decide the depth and the width of the window, and the type of gas in the air cavity, but everything was there was a set of parameters and everything was fixed. But here we had different designs, each of them with a different number of layers. For each of the layers, we had to choose among different materials. So basically, it was very difficult to come out with a direct encoding for solutions here. I'm of course open for suggestions if you have any. So we decided to go for indirect encoding. So we used one encoding that models the U coefficient of the constructed system, the thermal conductivity coefficient of the system, and we added some parameters such as the average density of the system. With this information, we try to find if in our catalog of constructed systems constructed with combinations of designed materials, which one was closer to meet these values. The problem with this is that there were collisions. There were different designs that have the same properties, the same U coefficient and the same average density. So we also tried assigning each of these combinations of materials and layers a sequential index. To make things a bit easier for the optimization algorithm, we sorted them by the thermal transmission coefficient to somehow soften the search space. And we also try to add the type of facade, if it's a ventilated or a ETICS facade, the average density of a combination of both. So, well, that's what I mentioned. Now, these are the results that we are obtaining. The algorithm is able to search with all the encodings, but with some of them it's more difficult. When we only use the index or the index plus the type of facade, it converges very, very fast. So we are now considering which is the effect of having those collisions when we use the U coefficient to represent the type of constructed system, and if that could be a problem for the other objectives, because in the end, from an energy efficiency perspective, it doesn't matter if we select one or the other because both perform the same. But when we include other objectives such as the cost, choosing one constructed system against the other would lead to the different cost. And if the algorithm cannot make a difference when we only consider the U coefficient or the U coefficiency plus density, that could be a problem. So this is something that we are trying to solve right now. And this is also similar for ZEB. So encoding here is a big issue for this part of the envelope. This is something that we also expect for roofs. So we are working on this. And regarding the results and the most scientific part, not this technical encoding part, we have found that the algorithm is also able to find reasonable solutions. That means that for locations in which ETICS facades are normally used, it suggests using this kind of facade. And for those locations in which opaque ventilated facades are normally used, such as León, and especially in the case of Seville, because of the high humidity and warm summers, it is suggesting this kind of facade. So even with these challenges regarding the encoding, it's able to find good solutions, something that final users can accept, because this is one of the problems with this kind of projects. In the end, we want architects to implement this, and they must feel comfortable with these suggestions, and they do with the results that we are providing right now. I'm running out of time, so I will be pretty fast in this part. It's just a mention, just in case somebody is interested in how we run these experiments. We are programming everything in Python, and we, of course, are parallelizing things with DAS. We run multiple runs in parallel, and we also run each simulation of energy plus or radiance for the solar comfort also in parallel. And I have to highlight that every fitness evaluation implies running simulations for energy efficiency, for solar measures through the year that affects the comfort of people inhabiting these buildings. And we need to gather all these results and combine them into a fitness value. We also use Git to keep branches for each of the experiments, and we prepared all the simulation environment within a Docker image that then is run as a container for each of the experiments, and we just fetch the appropriate Git branch within the container and run everything. In our current hardware setup, it takes like 20 to 30 seconds to run each simulation. Well, not simulation, it's fitness evaluation. So we can make a full set of experiments in less than 1 day, which is fine. But this is a very simple building design. So we should scale things in the future for real demonstrators. And finally, as I mentioned before, we want people, final users, to use this tool in their design, not only for the demonstrators that we have in the project, but also by final users. So we are aiming at a tier 7 maturity level for this tool, and I just provided some screenshots of how this tool looks like today. We have support for multiple projects. Of course, the simulations are not intended to run locally in the computer of the designer. So we have a distributed architecture here. The interface connects with the server and runs the simulation there, and then gathers the results. And those results can be further analyzed. The user can provide all this input information, the location and weather data. She can provide also she can filter the materials to be considered during the optimization. And well, here we have some details about how the glazing systems are defined, but we can also play with facade, with roofs, floors, HVAC systems, and renewable power sources. And here we have a detail of the optimization of windows, all the parameters and constraints and restrictions that apply. Once we have finished the optimization, we return the results, and all those results can be visualized. So we can represent on top of the model the solutions that we have obtained, and we can play with that. So this is a set of solutions with different window designs, different sizes and efficiency levels. We can also play with this shading system that I mentioned before. We can get into the detail of one solution, analyze what happens, for example, for a particular window, as in this case, see which is the recommended size, their properties, and so on. And we also provide some analysis module to compare solutions. The values that you are observing here, I don't think, at least for the parallel plots, I don't think those are real values. This is just a mock-up, but this is something that it's working now with real results. Sorry for the rush in the last part. To conclude, we need to expand our optimization to other components of the envelope. Now, the only part that is missing is roofs. We need to integrate renewable energy sources and also realistic HVAC models. We have already this defined, and we are now working on the integration of things, because this is done in a different library. Also integrating IPCC RCP scenarios. The use of surrogate models is also implemented, but not purely used, because these are not very complex models to run. And of course, try other optimization algorithms, especially multi-objective algorithms. Even if our final users will still want to control the weights of the objectives and to provide their own expertise in there, from a scientific point of view, I'm of course interested in trying them. So thank you for being here today. Thank you for your patience, and sorry for being a bit late. If we have time, of course, I'm open to answer your questions. So thank you again.
Okay, thank you very much, Professor LaTorre. So if anyone has a question, then you can ask now. Or you can type in the chat. Okay, I have one question, Professor Antonio. So is this simulation, I mean, how long, if I were to use this as an architect to design a apartment, how long does it need to do the computation to get an answer for me that if the design is good or bad?
Yeah,
in the real time.
It will depend on the complexity of the building. I can give you the time estimate for the apartments that we are optimizing now, which is this single apartment with 2 bedrooms, a living room, a kitchen, and a bathroom. We run 15 simulations for the 3 different locations, and it takes less than 1 day. So this means that each run takes like half an hour, let's say. Yeah, because it's 45 runs, 24 hours. Yeah, less than half an hour for one simulation. If we run just one simulation and just get the results of that run, because now we are running multiple times to have enough information to conduct a statistical analysis. But when you are using this as a final user, you probably won't be running this multiple times as we are doing now. And of course, you are not running it for different locations. You are running it for the locations in which you are constructing the building. But it will depend. It will depend on the complexity of the model. The thing is that it's something that will not last more than a few days, and so this is in line with the timelines of design projects in construction.
Okay. Yeah. Is there any other question? Anyone? Okay, there is a question from the audience. He asks, does the performance of the model change with climate of the area, or does it adapt effectively? You can see in the chat as well.
Yeah. I'm reading the performance of the model. I don't know if I understand to which model you are referring. If you mean the model the model of the bias of the simulations versus the monitoring data, this is something we are analyzing now. But it seems that we can create an aggregate model considering different locations and different types of buildings, and it mostly works to other locations of buildings. If you are referring to the final design reported by the optimizer, the designs are different depending on the location. Window sizes and materials are completely different depending on the weather conditions of that location. Yeah.
I think the second question is the same, so we're just gonna go to the last question, which is, can we adopt machine learning in this case?
We are actually using machine learning for the modeling at 2 places, for the modeling of the error of simulators, as I mentioned right now, and we also are using machine learning models to create surrogates for the simulations themselves. So to avoid running energy efficiency simulations every time that we create a new solution, we instead can use these surrogate models. Of course, we need some time to warm up. We are using an online approach, so we learn a new surrogate while optimizing, and the first iterations of the optimizers always simulate the efficiency of the building. And when we have enough information, we train these models, and then we have some rules to decide whether we should be using the actual simulator or whether we should use the information provided by the surrogate.
Yeah. Okay. Is there any other question? Okay, now we got another one. Given the growing awareness of how AI and ML technologies impact the climate, how will Do you believe solutions like yours will be adopted in the near future, particularly by stakeholders such as developer, architect, and building owner who must balance cost stability and regulatory pressures? What do you think?
It is a long question. I don't know if I have a short answer for that. From our point of view, what we are trying to provide is an extra tool in the same way that they use BIM design software such as Revit or AutoCAD or whatever the tool they use. This is only a support tool, something extra that they can rely on to try to accelerate the design time windows of the project. So of course, running simulations like this that are costly and take some time. I mentioned before that probably for a real world case, it would take like a few days to complete. But if the designs are more efficient than those they could reach designing by hand, I think that it is much compensated by the resources, not only energy, but also physical resources that they are going to reduce when adopting this kind of design. So from that point of view, I don't think there is a stopping barrier there. I see more problems in the acceptance from users that are used to make things in a particular way, and there is always this resistance to change. It takes a lot of time to convince them, let's say. So in one of the last meetings that I had with one architecture studio, I had to be very soft, explaining that this is not replacing your design. This is complementing your design. Of course, you can provide your input everywhere in every aspect of the design. You can constrain how much you want every aspect of. If you want to use one particular HVAC system, you can fix that and try to optimize for the others. You can constrain the alternative designs for walls. If you don't want ethics walls, then let's play with prefabricated and opaque facades. So basically, you have control on the tool. This is not something automated that provides a result and then you have to implement it. You have the power to control every aspect and just let it help you. Because many times in some of the decisions they make, they rely on their past experience. They don't consider other designs. I have been doing this for 20 years in the same way, so let's continue doing this. And sometimes when you suggest some design alternatives, they say, okay, that makes sense. I would be eager to try this in my design. So you should be careful, but I think that they can, or at least some of them can in the end accept it. Yeah.
Yes, I think so. I think next question is from John Colorado. He asking, a good simulation depend on a climatic data. However, sometimes this information isn't current. What about this?
Yeah, and we actually have updated our climatic information during last week. One of our architects has provided new files released by the IPCC this last week. So we are going to rerun all the simulations now. We have updated files for Spain, for the UK, and for the Netherlands. I don't know. I'm not sure about Ukraine, but Ukraine is very complicated for many different reasons. But of course, this is very true, and this is more true in the case of the projections for 50 years from now, because these are projections that depend deeply on what we do and some interactions about the fixation of carbon and many very complicated things that I don't really fully understand, but that have a high degree of uncertainty. So they always provide time windows of time windows, some windows for those parameters, and they say, okay, the average increase in temperature in this scenario is almost 4 degrees, but it could be 2.8 or it could be 5.6, for example. So there is, of course, this uncertainty, and simulations have to account for that. But a manual design also has to account for that. So I don't see much of a difference here. We are doing an effort to integrate that. Yeah.
Okay, thank you. I think I'm just gonna go for the last question, and we should close the session. So the last question is, in the optimization process, how does the algorithm balance cost reduction against minimizing environmental impact? Is one prioritized over the others?
Yeah, in our current implementation, I think I mentioned that, but I was rushing a little bit, so it's normal that that this question arises. In our pure implementation, cost is only taken into account when we meet the heating and cooling demand imposed by regulation. So when we reach those reference values, then we start optimizing the cost, applying a penalty to solutions with a higher cost. If we don't meet regulations, we ignore the cost, and we try to get solutions into a feasible region, because if you don't meet the regulations, you cannot construct a building, of course. So yeah, but basically we are implementing this like that, and in the final tool, cost is one of the objectives, but I don't think we are going to change this these 2 steps procedure. Okay, we can assign a weight to the cost objective, but we also need to meet regulations. So while not meeting regulation, cost can be considered.
Yeah, okay. Thank you so much, Antonio. And thank you so much for everyone for coming to listen to us. And I think Tom has an advertisement for the next webinar, right? Tom?
Thanks, Anthony, and thanks to Antonio. Just wanted to let everyone know, hopefully they can see my screen. We have a QR code. Next Friday, we have a interesting panel, AI at the Crossroads, Navigating Regulation, Ethics, Inclusion, and Trust in a Fragmented Global Landscape. So we have a panel of leaders in the computational intelligence community who will be discussing the topic next Friday. It's 12 p.m. Eastern. Obviously, when you go to register, it will convert to your local time. So if you're interested, we encourage you to scan that now, and it will take you to the registration. We'll give it about a few seconds, and then we will close the webinar. But thank you, everyone, today for attending.
Thank you.
Thank you. So I'm just leaving. Okay, thank you, everyone. So good night.
Thank you. Bye-bye.